Okay, so let's start. Say we have a plane, okay, x and y, and you have a point on the plane, describe it as vector x, and say r is just x and y. Now, if you wanted to rotate this plane, okay, you use the rotation matrix, which you call r of theta, which equals cos theta sine theta minus sine theta and cos theta. Okay. Now, if you take the rotation matrix and you do a major multiplication on this vector, you get a new position. That new position will be this point rotated by some amount theta. Okay, that will be this new r prime. Now, this matrix, okay, satisfies a few properties, because for it to be a rotation matrix, it has to be an SO2 matrix. Okay, and so it satisfies the following properties. First, the transpose of r times itself is the identity, and second, the determinant of r equals 1. Okay, these two put together we call special orthogonal. So this matrix is special orthogonal. This essentially this represents the fact that the magnitude of the vector when you times it by this does not change. Okay, and this expresses the orthogonality of the matrix. Now, say you take the matrix. Next thing I'm going to do, right? So I first said we'll start off with rotations in 2D, and we'll go from here to Lie group. So how do we go from rotations in 2D into a Lie group? Now, one of the properties of Lie groups is that it's continuously connected to the identity. So the way to see this, and this is what I love doing. I mean, it's just so cool when I first do this. If you take the cos theta, sine theta, minus sine, and the cos theta, okay, we can rewrite this in such a way that it will just lead us straight into the result that we're looking for, right? Into the expression of the Lie group. So first thing you do is you expand each of these terms as a Taylor expansion. Okay, so what you get is 1 minus theta squared over 2 factorial plus dot dot dot. I'm not going to write any more than 2 factors minus theta cubed over 3 theta factorial plus dot dot dot. Minus theta plus theta cubed over 3 factorial minus dot dot 1 minus theta squared over 2 factorial plus dot dot dot. Okay, so just sine cos theta all expanded, and then what I'll do is I'll factor out each order of theta multiplied by the corresponding matrix that will result in whatever expression this is. Okay, so first you factor out the theta to the 0, which is just 1, 0, 0, 1, the identity, plus theta times 0, minus 1, 1, 0. Okay, you can see this because we have no factor of theta as a 1 in the sines, only in the causes, only in the sines, and so those are 0. Okay. Then you have theta squared over 2 factorial of minus 1, 0, 0, minus 1. Okay, this is just taken from the cos. And you keep on doing this for higher orders of theta. Now, the amazing thing here, okay, and you can see this for yourself, it's not a proof, this I'm just telling you and you have to believe me, is that if I take this matrix and call it J, the corresponding higher order of matrices will just be J squared, J cubed, and so on, okay, which is absolutely fucking mental, alright? So you can essentially write this whole matrix as just the identity plus theta J plus theta squared over 2 factorial J squared plus dot 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 and so on. Okay, Now, you can clearly see from this, okay, the thing to take away from this is we've written this matrix as the identity plus some higher order terms. So for thetas that which are very, very small, okay, you can ignore higher order terms and you get closer and closer to the identity. Thus, the where the term comes from when you talk about Lie groups, which are essentially they form manifold, differential manifold. They are continuously connected to the identity because they have this property that if you expand it, and you'll see, you just get the identity plus some first order, second order, third order, and so on. So the smaller the parameter you have, and the parameter in this case is theta, the closer you get to the identity. Okay, and this is one of the most important facts about Lie groups. Okay, and you can write this obviously as exponential of theta and j, which is just mental. I mean, it's just fucking mental. Like, you know, you have a 2 by 2, and this is exponential of 2 by 2, and the way that this whole process happens is just, yeah. And you will see how we can generalize this into much more complicated and complex things. In this case, we only have one parameter, and this thing we call the generator matrix. Okay, so this is the generator, and theta here is just the parameter. What is the parameter? The parameter is, well, the generator generates this matrix, right? You can clearly see it creates the structure, right? And it creates the structure needed for the Taylor expansions to separate in the appropriate way so that you have cos, theta, sines, and minus signs, okay? And so it generates this matrix. And what does the theta does? Well, if you pick a theta, then you're picking one particular element of this, okay? And because theta is continuous, you would say, you know, normally in group theory, the dimension of the group is the amount of elements if it's a finite and countable group. But since theta is continuous, you can't really say, okay, the dimension of the group is infinite. So in this case, we say the dimension of the group is just the amount of parameters we have. Okay, in this case, we only have one parameter, and you'll see how we can get more than one parameters from depending on the group you're in. We're just having one example. So here at the moment, we are going from rotations to Lie group SO2. Okay, and then we're going to generalize it, but not yet. First, I just want to do something quick. Say I'm only taking theta's really small, then this will be close to this matrix: 1 theta minus theta and 1. Okay, why is this? Why were they fascinated by this when I first saw it? Well, because you see that the generator is the thing that forms this, right? Because the generator is that minus and plus there, and that's where the thetas are. Well, say if you take the points x is 1 and y is 0, which is this point here, right? And you apply this matrix to that for a really small theta, right? So theta here is very much smaller than 1. What happens is this point goes to a new point, which is, it goes, you know, slightly up and then slightly to the left, okay? And you can see if it goes slightly up and slightly to the left, that is kind of the structure of a circle, right? You have to go up and left, up and left, up and left, up and left, up and left. So the actual generator has in it this structure which generates, you know, the circle-like property, which is just fascinating when you first come across. I mean, yeah, I would recommend you know, play around with this and try to figure out and go from actually properly the way you properly prove this. You need further mathematical expressions than just doing it to as a summary video, right? To say I'm revising in the future, I like to watch my own videos just to get the main idea. Okay, so we've just finished this. Okay, now I'm going to go into Lie groups in general. So I'm just going to generalize SO2, which is what we've done now, into SON and SUN. Okay.